some notes on this section. So what I think I'll do is I will talk through my notes, because if I write with this, it'll be so blurry, I don't think you'll be able to see it much either, and it'll start giving you headaches. Right, so can you all now see my notes on section 16.2? Right. Let's try and talk you through what the process looks like then. There are different kinds of line integrals. The first type we're going to look at is a line integral with respect to the length. And basically a line integral is, you notice how it's just a single integral? And its formula is f of xt yt multiplied by this weird square root thing dt. It's not unlike the arc length formula that you might have met a way back in the day when you were doing Calc 2. So I want you to imagine, what are you finding when you find these things called line integrals? That guy over here, see this fella here? He is the generic version of the line integral. So you read it like this: the line integral along the curve C of the function f of xy with respect to, in this case, the variable s, which is with respect to the length. Now, I want you to imagine that on the xy plane, you had a curve called C. So on the floor, there's a curve called C. Now, every single point in that curve, it has a y value of whatever this is. So you can imagine at each point there's a height. So what you're generating is, it's like a weird shaped curved fence, and the fence has a different height. And when you calculate this line integral, you're basically finding the area of that fence. So if you need a kind of visual, what the heck have I just got when the answer's 10? You've just found the area of this curved fence is 10. So that, you know, if a visualization or a concept, that might help you figure out what you're getting when you get it. When you're finished with these line integrals, the answer is a number, right? It's 42. Now here's a couple of tricky things. This analogy is good, but it's not perfect. It is possible to get a line integral of 0, and it's possible to get a line integral that's equal to negative numbers. Now, the analogy of the area of the fence doesn't quite work that way, but I want you to think of it like this. If the fence is above the floor, the XY plane, that's a positive area. And if it's underneath the floor, that's a negative area. So can you imagine a fence that half of it was above and half of it was below, and the two areas cancelled out and got you 0? The analogy there would be, remember finding the area under the curve in Calc 2. And the area under the curve could be 0, it could be numbers, or it could be negatives. Remember that? And we said, look, it's not like an area, it's an area under the curve kind of area. That's what this line integral is like. So we go with that as a concept. Okay. So this is the generic version. Actually, it makes a little bit more sense when you see an application of it. So here's an example of a line integral. Find the integral over the curve C of the function x over y with respect to s. C is given by this parametric curve, x equals t squared and y equals t cubed. And we're going to evaluate it from t equals 1 to 2. So can you imagine drawing a curve t squared to t cubed on the floor, right, the xy plane, and then the height of it would be the x divided by the y. So there'd be a fence, right? So you have this curved fence. So what do we do? Well, a couple of things. First thing, everything has to be converted into t's. Everything, right? So I'm kind of repairing this as we go along. There we go. So x is equal to t cubed. Then won't dx by dt be 3t squared? Y is t to the 4, so dy by dt is 4t cubed. So that's what's going to go here, and that's what's going to go here. Do you see the 3x by dt formula? This here is just a formula, right? It's just you apply it all the time. Now, what about the function xy? Because that's this fella here. It looks messy when it's written like this, but essentially you take the formula, in this case x over y, and you replace all the x's by this guy and all the y's by this guy, and then you make it look pretty. So in this case, x over y becomes 1 over t. We cool? Anytime you got a question, chuck it in. So, got another person joining. So the integral, this line integral, is going to be from a to b, which is 1 to 2, of this fella here, which is 1 over t, square root of this guy squared, plus this guy squared. That looks all well and good. Most of what I'm about to do now is pure process. It's just plugging things in and tidying them up. Right, so if you take 3t squared and you square it, you get this guy. You take 4t cubed and you square it, you get this guy. Now, let me hide this. This can help. Sometimes when you see the answer, it kind of distracts you from what you need to do next. So, let's just hide that guy. Right, suppose you were at that step there. You're trying to integrate 1 over t, the square root of that ugly guy. Well, you tidy it up a little bit, and it looks like this guy. So far, so good. Now you've got to figure out how you would integrate that, because you're going to come up with the practical problems of unusual integrals, things you may not have seen for a while. Maybe you haven't seen them since Calc 2, which could be a year ago even, right? So let's look at it. You notice that this, you can pull out a common factor of t to the 4. Let's see what the benefit of that is. Well, that leaves me with 19 plus 16t squared. See this t to the 4? It's inside the square root. Can't I take the square root of t to the 4 and get t squared and bring it out of the square root? When I do that, you get this fella. Now, that 1 over t times that t squared, well, they're going to combine, and now I've got a t. So do you see that this ugly guy here turns into a slightly less ugly guy here? Now we're pretty much at the end here. If we can get that integral, we've got the line integral we're after. We've got the area of the curved fence, if you want to call it that, right? Technique. What technique will I use to integrate that fella?
You said?
Correct. And won't it be 19 plus 16t squared?
Yes.
I hope you all see that, right? It's a u-sub situation. There are 3 possibilities that you're likely to meet in all integrations. U-subs, right? They happen a lot. Integration by parts doesn't happen quite as often, but occasionally they do. And then the third one is a really catch-all phrase. Power rules. I know what the integral of e to the t is, right? All those things, I know what 1 over t squared plus 1 gets me, right? It's inverse tan of t, right? That kind of thing, right? So the last one is just memory, really. I've done enough integrals and I know how to find them. Well, if you do that, and I've skipped a whole load of lines, but you can imagine that's what you get, and I know that's what you got because I checked it. So our integral, our line integral for this function along this curve ends up being that number. So I know it's not true, but can you pretend that this squiggly curve on the floor happens to be the parametric curve x equals t cubed and y equals t to the 4? If you think back to Calc 3, remember the parametric equations? X is a function of t, y is a function of t. At any given value of t, then you can plot a point. Imagine that's the floor. We have just found out that the area of this curve fence is that ugly term. A couple of people in various classes from time to time come up with an idiosyncrasy of the homework, and that is that there may be more than one way to write that answer, because there is. In this particular example, do you know I put the 48 on the bottom? Couldn't I have called it 1/48 and then in brackets did that guy? Couldn't I have brought that 73 in inside and called it 73 to the 3/2? I mean, just to mention 3 ways. The idiosyncrasy might be that you've got the correct answer, but it might not be quite the way that the textbook software expected it to be. So if you know that you're right, but it's said you're wrong, will you shoot me your version of the answer and I can just update your homework grade and give you the points for it? Because, you know, you have done it correctly. It's not that you've made a mistake. It's just that the software hasn't caught up with you. Okay, that is our first example then of doing a line integral. How do we make it happen? We take x and y and replace them by their t's. This ds here is basically that bit there, the square root dt. That's what ds is equal to. You put it together and you will end up with an integral, a single integral in t. Well, let's look at our second example then. This one is less information. We have to evaluate a line integral, xy, with respect to its distance, the ds version again. The curve is the right-hand half of a circle with equation x squared plus y squared equals 16. That's it. That's all you got. You have got to come up with the parametric equation of the right-hand side of a circle with that equation, right? That's going to be a, you know, your x and your y equals functions of t bit. Well, have you any idea how you're going to do that parametrically before I show you?
You can do x equals r cosine t.
Yeah, so the r will be a 4, so it'll be a 4 cosine t and a 4 sine t, right? So if you ever see a circle, think of r cos theta, but the r will be a number and the theta will be a t. So it'll be 4 cos t, 5 sine t, you know, things like that. Well, in this case, let's cut to the chase. Here's a little picture. I find it helpful anyway to draw pictures. So there's my little picture of what the right-hand side of a half circle looks like. And they're talking about the orientation. We haven't dealt with this yet, but the way you move along the curve actually affects the answer. If you move in one direction, the answer could be 10. If you go through the curve but in the opposite direction, the answer will be -10. It's the equivalent in Calc 2 of doing the integral from 1 to 4 or the integral from 4 to 1. Don't you? If you switch the numbers, you switch the sign. So the orientation is important for these because you might not get the orientation correct. You do everything perfect, but you don't start at the right t number and finish at the right t number. And so you get -42 and the answer is +42. Or you get +42 and the answer should be -42. So a little thing to watch out for. Right, so there's half a circle. Now, if you're only going to do a half a circle, don't you start with -pi/2 and finish at pi/2? So do you notice you had to start with a really ugly -1/2 pi, and then the angle curves all the way around to vertically upwards, which is a positive. So I have my x, I have my y, I know the start and finish values, and I already know what f of xy is. So the rest of this process should be pretty much standard. Let's see how it works. Right, x is going to be 4 cosine t, so dx by dt is -4 sine t. There's your y, 4 sine t, so that's its derivative, dy by dt. There's your function xy, that's going to be the x's, and that's the y's. Put them together, you get that. Pretty standard. Right, let's see what all the pieces look like when you stick them together inside the line integral formula. Well, it's going to be the integral from a to b, that's its generic version. Let's look at it when it's got some numbers attached to it. -pi/2 to pi. That bit there is the function. This bit here squared, this bit here squared. Now, a lot of trig things going on here, but actually quite a lot and very nice things happen. If you square that, you get 16 sine squared. If you square that, you get 16 cos squared. It's all about algebra, trig algebra in particular in this question. Isn't 16 sine squared plus 16 cos squared a really cool thing? What's it equal to?
16.
Yes. Life is so easy when things like that turn out right. So square root of 16 gets you 4, and now you're looking at, eventually, let's go a little bit more, 64. And unfortunately, I've told you what was going on, but see, to solve this question here, the 64 sine t cosine t, couldn't you use a u sub to do that? Agreed? And you'd get the answer eventually. This particular question has another opportunity. Do you know you could have rewritten it as 32 sine 2t if you used one of the trig identities and get the answer that way? Now, something remarkable happens when you solve this particular integral. Something you might not have expected. The answer is 0. This particular line integral is 0. Now, I said just the analogy is like area above the curve, right? What's happened is, if you imagine this as being a curved fence story, half the fence is above the x-axis and the exact same amount of fence is under the x-axis. So the areas essentially cancel out and you get a 0. So it's okay to get a 0 in these questions. There's an example of it happening. Or maybe that didn't freak you out. You're kind of used to weird numbers happening in calc. And that's my little analogy there. Okay, our next example. Suppose you're being asked to evaluate a line integral of this format. Now, the first one we got, they gave you everything. The second one, we had to create the parametric equation of that half circle. This time, we've been told that you're adjoining 1, 2 to 3, 8. So basically, it's a straight line. So your line integral is the integral over a straight line of the function x plus 4y. Now, like every starting point to these questions, you need to find a parametric equation for the line joining this point to that point. It's actually just part of a line. It's called a line segment. Now, I know how you get the equation of a line joining 2 points. Whenever you do anything in math, there's a hope in some people's mind, oh, I'm glad I've done that. I can now forget it. I'm never going to use it again. Everything you've ever learned from Math 99 onwards, from time to time, will pop in to your higher level math work. How long ago has it been since you've had to find the equation of a line joining 2 points? That could be a long time, right? Because you've been doing such clever math. Hey, a baby question like joining, the line joining 2 points. Does anybody know, I'm about to uncover it, how you actually do it?
A difference equation.
Okay. Now, that's my version of it. Y minus y1 equals m, x minus x1. Does that look familiar to you? You might have called it y minus b equals mx minus a. It's the same thing. Right. Now, if we just go through the fact that the slope here is 3, how is it 3? Well, if you do y2 minus y1 over it, do rise over run, right? Trust me, it's 3. Yes, it is. Just making sure. Now, that's the equation of the line, but I don't want to know the equation of the line with x's and y's. I want to know the parametric equation of that line. So that's a different thing we've got to do. We've got to figure out how to make that parametric. It's actually dead easy. One of the few things that are dead easy in this section. Here it comes. To turn any equation, including a straight line of the form y equals into parametric, just make x equals t, and then y just becomes 3t take away 1. So straight lines are easy, aren't they, right? 5x plus 1, right? If y was 5x plus 1, x would be t, and y would be 5t plus 1. That makes sense? Now, here's a little issue. We also need to know that that's 1 to 3. Where did that come from? I mean, I pulled it out of mid-air and said, here it is. But where did it come from?
Is it because you set t equals to x, and x goes from 1 to 3?
Mm.
Nailed it. You catch what you just said? In fact, you said it better than I was going to say it. You made it go from 1 to 3, right? X goes from 1 to 3. X is t, so t goes from 1 to 3. So that's pretty straightforward, right? Whatever the x value you start, whatever the x value you finish. Right, now you put these pieces together. Here we go. X is t, so its derivative with respect to t is 1. Y is that, its derivative is 3. You can't get much nicer than numbers. F of xy is 1x plus 4y's, which is this guy, which I believe is 13t take away 4. Right, that's all the building blocks. Put them together now. There's the generic equation. This is it in this example. You go from 1 to 3. This bit here is the f of xy, and this bit here is all that square root stuff. Go through this pretty quickly. You get that. I pull out the square root of 10, integrate that the usual way, and the answer is 44 root 10. So that curved wall would have an area of 44 root 10s. These questions where you're being asked to find a line integral with respect to the distance, that's what ds means, with respect to distance, right? That's how you do them. You feel comfortable about any of the questions that you might come across that says integrate x squared plus y squared ds, and then they go and tell you some curve c to do it on. Find the parametric equation of c, right? Find it all in t's, including the start value of t and the finish value of t. Plug them into that ugly formula up here, and what you end up with is a calc 2 integral in t, right? Just a single integral from calc 2, and you'll do your u subs and your integration by parts and your power rules and all the other things that you would typically do to finish the question off. So if you can get all the pieces, normally that's the hard part, right? Once you've got all the pieces in place, the rest is kind of a bit of tidying up and then calc 2. So, pause for a minute. Are there any questions so far about what we've covered? I'm going to close off for a second, because when I'm in this mode, we don't always get everybody who wanted to join. Okay, it looks like we've got everyone. I'll go back to sharing. Are we good? Last chance? Okay. Let's see what other types of line integrals, because there's more than just the one I mentioned. There's, in fact, about 4 different applications of them. Let's look at a line integral now, not with respect to distance, ds, but just a line integral dx or dy, something like that. Just a single variable. So an example could be this guy. Suppose you wanted to find the line integral of xy e to the power of yz with respect to y. Now, C is a parametric curve, but in this case, The parametric curve is in 3 variables, x, y, and z. That's very like Calc 3. Remember those funny helixes and things that you would get in Calc 3 when you did a parametric equation? Now, the line integral stops having a physical meaning anymore. I can't really talk about a 4th dimensional wall in 3-dimensional space. Well, I could talk about it, but my brain would hurt. So all you have to do now is say it's an algebraic process, right? This is how you get line integrals. So if you needed some kind of comfort in thinking, oh, well, I know what it looks like, what I'm getting, and that kind of disappears now. But that's disappeared before. Isn't it impossible to imagine a triple integral? You know, what is it? Because it's actually a 4th dimensional thing, right? You can't. Oh, or maybe you have unusual brain and you can. Okay, then. In this case here, the y is 2t squared. So watch how I approach this one. I'm only interested in this dy, so I'm only interested right now in the information that's here. The other stuff will come later. Now, if y is 2t squared, if you differentiate that with respect to y, doesn't dy by dt get you 4t? Great. Now you might think, well, how's that going to help me? Remember, the goal here is to turn everything that you see here into t's. Everything. Now, I know how to turn x, y, and z into t's because you told me it, right? I know it's going to start at 0 and t equals 1 because you told me over here. In fact, the only piece of the puzzle that's missing is, how do I turn dy into something with t's in it? Remember u sub? You had a line that looked something like this. If dy by dt is 4t, isn't the differential dy 4t dt? Do you see we now have what dy is in respect to t? I'm not calling that a substitution. You, if you like to call it that, you would. I wouldn't. I'd just say it's a differential. I'm changing it into something I can use. Are you okay with that jump? Does it seem reasonable? Yeah, okay, good. So there is our line integral that we're being asked to calculate. Hopefully I got this right. I believe I did. That 4t is the x. That 2t squared is the y. That's e to the y, the 2t squared. 3t cubed is the z, followed by a 4t dt. And the 4t dt was what the dy was equal to. So you see, everything has been turned into t's, which means that we are now looking at a single integral, a Calc 2 question. Now, I've still got a bit of work to do before I can get the integral. For instance, if you multiply everything together, you get 32t to the 4 e to the power of 6t to the 5 dt. And I wish I hadn't done that, but could you have recognized that that is a u sub story? If I just said, integrate this horrible mess, do you notice that if you make your u sub 6t to the 5 with a bit of extra tweaking, it works, right? It's a u sub question. In fact, if you do u sub on it, that's what the horrible answer ends up being.
Should the blue text there say 6t?
It should.
Okay, I just want to make sure I wasn't messing something up.
No, but I'm glad you caught it. These notes were made, this is like hot off the press. In fact, the notes aren't finished. And I wasn't intending to show you the notes. I was just going to make that as a PDF and put it online for you later. But since this thing is refusing to focus, I think this is working well. Actually, it's cleaner than my writing is, so in a lot of ways it's probably better than my usual way of doing things. That's my opinion. Okay, here moves. Suppose I asked you to do an even weirder line integral. This is a line integral on 2 variables. We're doing this fella with dy plus this different fella dz. Now that's weird. You've never seen a normal integral dx plus some dy's, right? You always had a single variable, in Calc 2, this guy dt, this guy dx, this guy dp, but never this kind. This is just an abbreviation. This means the same thing as this, which I'm about to type in, since this is notes as they're being built. So this fella here actually means the same thing as this fella. Now, when you see it that way, does it make a little bit more sense that what you're actually doing is you're just finding two line integrals with respect to a different variable? And I guess it's the classic thing in math of, to save me having to write one more integral symbol, we stuck it together as one big question rather than separate it out into what it really is as two separate questions. Now, all you do here then is put all the pieces together, but you apply them to two different integrals. So in this case, since I need this dz guy, oh, by the way, I've already found this guy, right? He's equal to this. So I'm not going to do that again, right? But I'm going to get this guy now. So z is my variable. So hopefully that's, ooh, okay, I can't count. Let's check who z is. Well, as I said, I just started that guy. Now he's correct, 9t squared. Which means that this fella is 9t squared. Now you put this package together and you get the integral of this, which is just a repeat of what was above, and this fella over here, which is 9t squared. This guy we've already got. Let's check this fella, and that's going to change some numbers around, isn't it? It's going to be 32 now. And I believe this guy is going to be 18 now. Okay. Now I'm just going to pause at this bit because there's some changes that are going to have to be made to the next one. I don't want to distract you. If I get to this point here, or if you got to this point here, do you feel comfortable that you would do a U sub on this if you hadn't seen it in your life before? And what would you do to integrate this second piece? It's not meant to be a trick question. What would you do to integrate 32t?
Wouldn't it just be power rule for the second part?
Yeah, sometimes you can talk yourself out of doing the obvious. Yeah, it's just a power rule. Ugly, but actually not as ugly as I think it's. Yeah, it will be. It'll be ugly. And you get what you get. And those numbers there are now going to be wrong because I made a mistake in one of the values. Are you comfortable about a line integral now that might have a dx on it, right? An integral of c of some function dx, or some function dx plus some other function dy plus some other function dz, right? You could have a line integral with all three x, y, and z in it, or just x in it, or just x and y in it, or any other combination. The process is turn everything into t's, and then it just becomes a Calc 2 question. So let's see what our next cell is. Right now, we haven't given you much in the way of practical reasons for why you would want to find a line integral. We're going to look at, in particular, a line integral of a vector function, f, along some curve C. Those line integrals where you've got a vector function and a curve, what you very often are going to be finding when you find these line integrals are things like the total work that you would do if you were moving along that curve C. And the vector function f is the vector field. So you remember that picture where all the little funny arrows was representing, saying the wind blowing in various directions? And you can imagine the curve C as being this aircraft flying through the wind. And what you would be calculating when you calculate the line integral would be the work that would be required, right? The energy that would be used in traveling through that particular pathway. So line integrals are very often used in calculating the work done in moving an object through some kind of force field. And it can be all sorts of force fields. You know, you can have a magnetic field and you're just moving a piece of, you know, a little piece of wire through a magnetic field. You might want to know how much work would be done. It can be done to you. In other words, you can pick up energy, which I believe is what happens. If you take a coil of wire and you move it through a magnet, around a magnet, doesn't that generate electricity? A very crude way of doing it. So I strongly suspect that that would be an application of this kind of question. But don't quote me on that because I'm not a very engineer person. Right, so here's a definition for you. Let F be a continuous vector field, right? C is a nice normal curve. And we describe C in its parametric form. So see when I was saying earlier on x equals t and y equals t cubed and z equals sine t, that is basically the parametric equation of the curve. So that there is just a shorthand representation of that situation. And t is, say, going from a value a to b. Then the line integral of f along C is given by this notation. You see that funny little dot between the F and the dr? You see that? Now, they're bold. In textbooks, vectors are bold. I do little arrows above my vectors because when you do them by hand or in text, bold doesn't show well. Do you know what that dot represents? Because it is a specific thing. What you've got is a vector F dot a vector dr. I've almost gave it away the way I said dot.
It's a dot product.
It's a dot product, right? So what you do is you find your vector field F in terms of t, you find dr in terms of t, and then you do the dot product of them, and that's how you get that particular kind of line integral. So that's the theory behind it. Let's see if we can actually do one. Suppose you're being asked, oh, this is unfortunately going to be our last one today. Suppose you are asked to evaluate this line integral here. And they tell you that the vector field is this guy here. Are you comfortable with the IGI notation for vectors? You know, you've got the other one that looks like less than and greater than symbol as well. But we'll stick to their notation. So this is your vector field. So any given point x, y, and z, so this is a three-dimensional vector field, the vector would be pointing in that direction. Now the curve, the parametric curve that's traveling through this vector field has this parametric equation. Now you got to understand how to translate this. See the t squared next to the I? That is telling me that x equals t squared. See this t cubed next to the j? That's telling me that the y is t cubed. And see the negative 2t next to the k? That is telling me that z equals negative 2t. So I could have told you that by saying the parametric equation of the curve C is x equals t squared, y equals t cubed, and z equals negative 2t. But in this format, it works better in context. So I'm going to convert this fella into t's. So let's see what that looks like. And we're going to keep it in its vector notation. So x plus y squared, the x and the z, and the y and the z, and this is what it ends up looking like. So that's how you would represent the vector field or function fxy being turned into t's. Are you comfortable about how you got the x, the y's, and the z's and y now is in terms of t. Now, the other piece of the puzzle that we need to figure out is how to get this weird derivative. It's not dr, it's d vector r. Well, let's show you who we have. There is r. If you differentiate vector r, you get that guy. And the fella that we call d vector r, right? So where is it? Lost my guy. Oh, where is he? Yeah, there he is. See that guy there? He is, in fact, the derivative of r dt. So if you know the parametric curve, just differentiate its components and stick a dt at the side, and that's you. You're good to go. So if you take this guy, you get 2t. You differentiate this guy, you get 3t squared. You differentiate this guy, you get -2. So this is the parametric equation of the curve, and this is the parametric equation of the derivative of that curve. We go. Now, dot product of those two fellas. That's the f of x, y, z. This is the curve derivative of it. That guy, dot product, that guy. Messy mess. Multiply it out. Collect like terms. It ends up looking like that. So can you imagine it's just going to be messy calculations. Remember how the dot product works. The x component times the x component plus the y component times the other guy's y component plus the z and z, right? Well, in this case, it ends up being that fella. If you do power rules on this guy, ends up being 8. So if you wanted to know, the question hasn't been phrased this way, but if you wanted to know how much work would be done in this vector field here, moving along this curve, starting at 0 and finishing at 2, the answer is that the work required to do that would be 8, whatever the units of work are. I think, is work units newtons or newton meters, or what are they? Engineers amongst you, what's the units of work?
Newton meters.
Newton meters. So that would be 8 newton meters probably, right? Are we good? Are we feeling a little bit more comfortable when you start looking at these line integral questions, that your goal is to turn everybody into a t? And you need to know what the curve is, the c, in terms of t. If they tell you what it is, great, go for it, right? But if they don't, like some of the early questions, then we have to find the parametric equation of the half circle and the parametric equation of the straight line. So occasionally you have, that's an extra piece of work where you have to figure that guy out. I don't know, I think, I know your time is valuable. Can we try one last one? It'll be a kind of quick version, but at least it gets, you know, hopefully you get something out of it. So here is definitely our last one. And I was wanting to do it because it has a work done story to it. So find the work done in a force field. This is a nice 2-dimensional, so it's a little bit less work. Moving along this curve. Right, so we got pretty much all the pieces that we need. Step 1, turn everything into t. So here's the force field function. Replace the x with t, take away sine t. Replace the y with 1 minus cosine tt. Are you comfortable that that's what it would end up being? So the x plus y plus 7 ends up being this. Now we have a parametric curve. That's c. That's its derivative. Right? Differentiate. Differentiate. That's me got pretty much all the pieces that I want. The work done is the line integral of the vector field dr, which we transfer to the r dash dt version, which then becomes the integral from 0 to p of this guy. That's basically your f dot your r dash dt. Now you do the dot product, x's with x's, y's with y's. You multiply them out. You collect like terms. And you're kind of looking at this fella. So we are now at the point where Calc 2 kicks in, right? Once you've done all the tidying up, basically you've got an integral in t. In fact, you're always going to have an integral in t in this section, right? I know how to do t. I know how to do the integral of sine 70. How am I going to do a t cosine t?
Integration by parts.
Okay, who are you going to make the, well, some people do it as uv, some people do integration by parts as f and g. Who are you going to call f and who are you going to call g? We do it that way.
Wouldn't the t be the f and then the cosine t would be the g?
Correct. Do any of you do the uv version of integration by parts?
Yeah, I do that one.
Right. How would you say it in the same, how would you say it in uv then?
The u is the t and then the v is the cosine t.
Oh, so not that big a difference, I guess. Right.
It's just different letters.
Different letters. Okay, so you can handle it, right? I didn't do this. I just plugged this into Mathematicus, and it told me it was 2 pi squared, so I'll believe it. Right. But there's a few lines of working in there. Topic. Suppose it's work done. Let's see what is allowed in work done. 2 pi squared is fine, right? It's an exact value. Nothing wrong with that, right? It's about 18, 19 units of work. Could you get 0 as work done? Yeah. Work done in 0 would be pushing a big thing up to the top of the hill and then pushing it, well, not so much pushing it back down, getting dragged back down on the way back. Wouldn't the net effect be 0 work? You get the work, if there was no friction or anything, you get the energy back that you put into the job, right? Could you get a negative work done? So I'm just saying this so that when if an answer that's negative comes up, you don't freak out. Is it possible to do a work done question and have a negative answer? Yeah. It would have to be a story where whatever you're doing, you gain energy, right? You gain something from it. Has anybody got an analogy of a negative work done? Because I can't think of one off the top of my head.
Pulling up versus pushing down.
Okay. Pushing down, you get energy out of it, I guess, because it's actually doing it for you and you're not doing anything, are you? You're just hanging on as it drags you downwards. So I guess that would be negative, right? Kawika's turned up at a really interesting time. I did say 11, didn't I? Because you're all here at 11, so it must have been, right? Okay, that is it. I'm going to fix a couple of things. What I didn't have time for is I didn't have time to show you an example of finding the center of mass using line integrals. The story in that case will be a bent piece of wire, and you're trying to find the center of mass of a bent piece of wire. It's an application, it doesn't change too much. I'll have a look at the homework and see if there's anything else, but I think that's, yeah, I'm pretty sure that's me covered all the likely situations that you're going to need to do for line integrals. You won't get this online for a while because I have a class to take, which I'm actually talking far too long here. I have to go. So bye-bye, everybody. Have a nice day.
Well, dang it.
Thanks.
Right.
Thank
Well,
you.
thank you for turning up, Kawika, but you missed all the good stuff. We learned some.
Had my standard 10 o'clock class today, so I was hoping this one would be at 11, but then I double checked the time. It was 10 o'clock. I was like, no.
That happens. I understand. Right, I'm going to have to disappear quickly because I have a class at 11 that's a Calc a trig class, so won't be much point in on you doing that.
Fair enough.
Okay. Right. Well, I'm out of here. So bye bye.